Now we want to address the idea of LU decomposition. We're going to do this in a little broader context where we completely reduce this matrix using elementary matrices, but then we'll see just what LU decomposition comprises, which is actually quite a bit simpler. Okay, so we have the matrix A, 1, 2, 4, negative 8. This matrix is non-singular, as we found in previous videos, so it's, in other words, invertible. And we want to invert this matrix using elementary matrices. Okay, so the complete reduction is as follows. Okay, now we look at the rows and we see that adding negative 4 times the first row to the second is going to give us a 0 here. So it's very easy to see, of course, if we just look at the matrix, and we've done this very recently, so in very recent videos, we see that this reduces to this, okay? And then this, multiplying through here by negative 1/16, reduces to this. And then adding negative 2 times this row to the first row gets us down to the identity. So just in 3 simple steps, we manage to reduce this matrix to the identity. Okay, but we want to do this with elementary matrices because elementary matrices are very simple and they're very easy to invert, and we can use the elementary matrices and their inverses to find the inverse of the matrix A and also the LU decomposition. Okay, the LU decomposition can actually be done as soon as we get to this stage, but we're going to go through the whole thing. Okay, so okay, we want to add negative 4 times the first row to the second and replace the second. And how do we do that? Well, we can use the elementary matrix that we get by doing the same thing to the identity. So if we do this operation to the identity, multiply negative 1 times the first row, add it to the second, it's clear that this is what we get. And then the inverse operation, the operation that would take this matrix back to this one, is what? Well, if we add 4 times the first row, well, again, down here, if we add 4 times the first row to the second, we're going to get back to this. So we got this by subtracting 4 times the first row from the second, starting with this matrix. If we take this matrix and add 4 times the first row to the second, since we haven't changed the first row, we're going to get back where we were. So the inverse operation is to add 4 times the first row to the second. If we do that to the identity, we get this. So here's our first elementary matrix. Here's our second elementary matrix. We also note that the determinant of this one is 1. The determinant of this one is 1. Okay. Now, one thing I'm going to do, since I want to do LU decomposition, is I'm not going to do a lot of switching of rows because switching rows introduces superdiagonal matrices, and we want to stick with subdiagonal matrices, lower diagonal matrices. And we notice that these elementary matrices are lower diagonal matrices. Okay? Well, anyhow, if we take this E1 matrix and multiply it by our original matrix, we get the matrix that we got if we added negative 4 times the first row to the second. So multiplying by the matrix that you get from the identity by adding negative 4 times the first row to the second gives you the same thing as just adding negative 4 times the first row to the second. And you might wonder why we go to all this trouble, because we learn a lot about the structure of matrices, and ultimately we gain facility that we don't otherwise have. Okay, we gain options. We among other things, we could do LU decomposition. Okay, well, now what do? We want to take this matrix. What's our next step in reduction? The obvious step is reduce this so that we have a 1 here. And so we do that by multiplying the second row by negative 1/16. Well, we do that to the identity and we get this matrix. And then we note the inverse matrix. Well, how do we undo multiplying a row by negative 1/16? We multiply it by 16. So we multiply negative 16. We multiply the second row by negative 16. in the identity matrix, we get this. This is our E2 inverse matrix. Its determinant is negative 16. This is our E2 matrix. Its determinant is negative 1/16. So, elementary matrix, second elementary matrix, inverse of second elementary matrix. Next step, let's complete this step. Let's multiply this matrix by this and see that it works out. Okay, so here's this matrix. Here's elementary matrix, your E2 elementary matrix, and we multiply it, and it gives us exactly the same thing as if we'd multiplied the second row by negative 1/16. We complete the reduction, looking for words here. We complete the reduction of this matrix. We need to get a 0 here, so we add negative 2 times this row to this one. So the first row is going to be changed to the first row plus negative 2 times the second. Now, that's what happens if we do this. We're going to get this matrix. Okay. The elementary matrix is going to be what we do if we do this to the identity. So add negative 2 times the second row to the first. We're going to get this. The inverse is, well, we add 2 times the second row to the first. Okay? And here's the inverse of our third elementary matrix. If we multiply our third elementary matrix by this matrix, we get this. Okay? Now I've got a couple of arrows in here that are kind of pointing to the wrong thing. The operation that we want to do on this matrix is this. We haven't done anything to this row, so actually this operation comes down and applies to the second row here. And then this operation comes down and applies to the second row here, and this operation comes down and applies to the first row. Could have been misleading, but if you understand the procedure, it's fairly easy to understand. Okay? And with a little practice, it gets quite easy to do this. Okay, well, what have we done here? Okay, well, I haven't left myself a lot of room again. What we have here is the matrix product E1 times A. Okay, now what do we have here? Well, here's our elementary matrix E2. And we apply that to this matrix, which is E1A. And then finally, we got our elementary matrix E3, which we apply to E2, E1A. So that the final matrix is E3, E2, E1A, and that equals the identity. Okay. Now what would we multiply? Well, this means that if you multiply two matrices, and I can put parentheses here, if you multiply two matrices and get the identity, then they're inverses. So that this is A inverse the product of these matrices is the inverse. Okay, well, we'll go on and talk about LU decomposition, but this video is getting long enough.